Okay, we see here the handheld generator. The wire leads coming out of the generator and separating here into the two clips. Okay, we see the two clips attached to the light bulb, and we see that as we crank the generator, we can light the bulb. If we attach to another bulb with different numbers on it, it might be easier or harder to crank. We might have to crank faster. We might not have to crank as fast. What's going on here? Well, we can represent the circuit maybe like this. This symbol here represents the source, and you can read about that in your text. There's conventions involved with the source. This represents the thin wire on the interior of this bulb. Now let's see if we can get up close. Can we get up close here? Camera doesn't seem to want to focus. Let's make sure we're on autofocus. We are. For some reason the camera doesn't want to focus that close. It should, but it isn't. Anyhow, if you look inside the bulb, you can see a little thin coiled up wire running across the bulb. And what's happening is when we crank the source, we're pushing electrons through that thin wire. And there are things that go on in that thin wire to make it resist the flow of electrons more or less. And if there's more flow of electrons, it turns out that we actually have to crank harder. And when there's less flow of electrons, we crank less hard. And we'll see some of that as we go through these ideas here. So, the same number of electrons in any given time will flow through both wires. Now we'll see later that electrons really don't like to be close together. Our charges don't like to be close together. They get as far away from each other as possible. And the implication of that is that there's no place in this circuit here where charges can actually be stored up. Meaning that what goes through this wire has to go through this wire and come back here and go back through the source. The flow of electrons is the same throughout this circuit. Now, if we have faster electrons, that means that we have more kinetic energy. Okay, so the faster the electrons go, the more the kinetic energy they have. Now, the electrons are traveling through wire, and the wire consists of molecules, and the electrons, as they travel through the wire, interact with the molecules. Now, one model for that, just to provide a little bit of information, one model for that is the electrons travel through the wire till they bounce off of a molecule. And that's really not a bad model. That gives us a very good, well, we can obtain some very good proportionalities out of that model and do a good job of explaining a lot of what we see here as if the electrons are bouncing around and just colliding with molecules and transferring their kinetic energy to the molecules. And of course, that constitutes a thermal exchange. Okay, if the electrons did just bump into the molecules, that would increase the vibrational energy of the molecules. Molecules sitting here, electron comes along, hits it, the molecule vibrates a lot faster. Or, well, maybe not a lot faster, but a lot further, with a greater amplitude. And therefore has more kinetic energy, more thermal energy. So that these faster electrons exchange more thermal energy with the molecules. And therefore lose more thermal energy. And in that case, we're going to have to supply more energy through the crank by cranking either harder or faster. In other words, exerting more force in the crank or turning the crank at a greater rate or some combination thereof. What actually happens in the exchanges between the electrons and the atoms is really a quantum mechanical process and more associated with waves. Okay, you've got this electron which basically acts a lot like a wave, and that wave interacts with the molecules and exchanges thermal energy. We're not going to get too specific about what happens there because the quantum mechanics is way beyond the scope of this introductory course, but you should know that when we do quantum mechanics in this situation, we're actually talking about waves, and that's one of the reasons that we study waves, so that we can later understand that quantum mechanics. Now, as far as a model goes, we could model this by having electrons in the thick wire, electrons in the thin wire. Now let's just assume that there's a constant electron density. That's not really the case with the generator and the bulbs, because the wire that goes up to the bulb is copper, and the wire in the bulb is an alloy of tungsten, I believe, and therefore has a different electron density. That is, a different number of electrons per cubic centimeter, cubic millimeter, cubic meter of material. But right now we're going to assume a constant electron density, and by that means the same number of electrons per cubic centimeter in this wire as in this wire. Just to simplify the model a little bit. Again, that's not always going to be the case. In most cases it won't actually be the case, but it's fairly easy to adjust for different electron densities once you understand what happens for the same density. Now this becomes a whole lot like the continuity equation in fluid mechanics. You have some average velocity of electrons here and some average velocity of the electrons here. You have as many electrons flowing past a point in this wire as you do past a point in this wire, meaning that these electrons have to be moving a whole lot faster than these electrons. The result is, again, that there's more kinetic energy per electron, more kinetic energy exchange in collisions, and therefore this wire gets a lot hotter than this one. Now in the case of a light bulb, the wire gets so hot that it emits electromagnetic radiation that you saw, light. Okay, it glows from the thermal energy, from being at a high temperature. It's giving off thermal energy, trying to get back to the temperature of its surroundings, essentially. Let's see, the one misconception that we might have here, and we've got to be careful about this, there are analogies here between the flow of fluid and the flow of electrons, but those analogies aren't always exactly correct. You might think of the resistance of the electrons going through here as being the result of just having less area here and having to move these faster. Okay, and that's pretty much true, but the length of this thing is also important. Obviously, if we have a greater length of wire here, there's more kinetic energy being exchanged in that length, and therefore it's going to take us more work to get the electrons through there at the same rate, assuming they go at the same rate. But if we have a greater length, it turns out that for a given rate of cranking, fewer electrons will actually flow through here. We might think of the reason we have to exert a cranking force is that we have to force all these electrons through this narrow opening here. And that's not a very good analogy. Because when we have to crank hard, that means that we have a lot of electrons flowing wherever they are. Okay, it's the number of electrons that flow in the different parts of the circuit. And a greater flow rate means that we have to exert more force. That's not exactly analogous to what happens with a fluid. Okay? At least not according to the continuity equation and Bernoulli's equation, where we have, if we take into account the friction with the walls of the fluid, the analogy gets a little better. Let me just warn you that the analogy isn't perfect. And as we go through this, you'll see some places where that analogy breaks down.